Start rolling. We're meeting today with Bob Saya, Vice President, Next Generation Product Family at Pratt & Whitney. Nice to see you again, Bob. I think the last time we did this was at Paris.
Yeah.
Can you give us an update on the Gtf program? We heard today that there's a new variant, 35,000 pounds thrust for the A321neo. You've now got 3 sizes, 5 customers, and at least a dozen applications from what I'm counting. Where are you with the program, and how are you meeting your numbers?
Okay, well, thanks, Ernie, for being here today. Overall, from a test program, we've tested about 35 engines. Got about another 5 or 6 that are in assembly right now. We have 9,000 hours of testing completed across the 3 engine models that we're developing, and about 1,300 hours in flight on our 747 flying test beds. We have 2 747s that we use across the models. So the program's been very, very active. We have a lot of activity going on. The C-Series engine was certified last year. We're well into the flight test program. The 4th flight test aircraft began testing, did its first flight on Sunday. And so we still have quite a ways to go yet in terms of supporting Bombardier to achieve aircraft certification, but the engines are running well and the program's going well. In the case of the A320neo, we're about 75% of the way through on engine certification. We'll certify later this year. We have just delivered the first 2 flight test engines or production engines to Airbus, so they're in Toulouse. They're being fitted with the nacelle system by UTAS, or the former Goodrich Group, to be installed on aircraft 1, and that aircraft will fly later this year. So overall, from a program perspective, the 2 engines that have really done a lot of testing, the C-Series engine and the A320neo engine, are performing well. All of the models, I can say, will hit their engine guarantees that we've made to the airplane manufacturers. So we're on track to deliver on the fuel efficiency that we committed to back in 2007 when we launched the first 2 models.
That's great.
In fact, the first 2 Neo engines are slightly better than the guarantee that we made to Airbus from our measure. We'll know that for sure when Airbus flies the aircraft later and measures, but we really believe we're on track. As a result of the engine running well on fuel efficiency, it also means that it's running well in terms of turbine temperature. So we announced today that we have established a new engine model within the PW1100G JM, and that's going to be a 35,000 pound thrust class variant. That offering is being made today to customers, primarily for operators that are flying in hot altitude conditions, like Mexico City, Phoenix, Bogota, where we know that the airplane can use extra thrust and stay within the aircraft criteria that's been set for aircraft certification. And we'll see if it makes sense to expand that thrust capability to lower altitudes as time progresses. Mm-hmm. As a result of this higher thrust, it does allow an operator today that may be operating A320s to convert to A321s because of the higher thrust, allowing an aircraft to carry more people. So it's a good opportunity for us. We're really pleased with our overall market share on the A320neo family. We're slightly above 50%, and well above that on the A321 variant.
Yeah, I think this will certainly cement that market share lead on A321.
Yeah, and I think the reason why we're doing so well on the A321 is because when we designed this engine, right from the beginning, we designed with the A321 thrust range in our focus. And with the engine operating well, we now are able to even expand that a little bit further, which is value to us as well as value to the airlines. And that's really our overall objective. And when we launched this program in 2007 with Mitsubishi and Bombardier, our prime focus was to lower engine operating costs by 20%, and we're above that today. So we're very, very, very pleased. From an overall next steps, we've got for the lower thrust model, the 17,000 pound variant that will operate on the Mitsubishi MRJ. Those two engines are in their final stages of assembly, and we will deliver the first two engines for aircraft number 1 mid-year, and that will enable MITAC or Mitsubishi to prepare that aircraft for first flight, and we're on track, meeting their overall program milestones. We've, as you and I have talked in the past, we've made some adjustments on our program so that we could ensure that we were timing it well relative to the progression of the MRJ aircraft, and we're still continuing to work closely with MITAC to ensure that we meet their overall milestones.
That's great. I know that while you're working on getting the production engines out for the 5 models that you're on, you're also working on the R&D for what you've called a second generation GTF.
Right.
How well will that second generation be as you increase the gear ratio from 3 to 1 today to perhaps 4 to 1? And what kind of fuel efficiency gains do you expect with that second generation of GTF engines?
Well, back a couple of years ago, we established what at that time we called a 10-year technology roadmap, and it was really targeted to take our current GTF, which we call first generation GTF, up by another 10% in overall fuel efficiency. And the 10% wasn't too magic. What we said is, looking 10 years out, we'd like to try to average, consistent with our industry past, 1% improvement per year. And to do that, we recognized that we would certainly be developing improved aerodynamics and improved materials, maybe improved cooling schemes for the combustor and the high turbine. But a key element of that was also look at leveraging the value of this geared architecture, going from a 3 to 1 gear ratio to as high as 4 or 4.5. So bringing the overall, what we call the bypass ratio, or this bypass air characteristic of a geared engine, from a 12.5 to something of 15 or even maybe approaching 18. And the value of that is that we just continue to expand on the leverage of the gear and improving fuel efficiency, and with the side effect also being lower noise and improved emissions. So we've established this 10-year roadmap. We've now advanced to what we call our second generation geared architecture that's targeting a 15 to 1 type bypass design. And we've done some maturing of several of those technologies, and the question will really be when and on what platform. So today we designed our initial models to cover a 15 to 40,000 pound thrust class for the single aisle. We've now conceptually defined a 70 to 100,000 pound geared architecture for a wide body application. I say it's conceptual because it's really more of what design space do we want this engine to operate in terms of temperatures, pressures, speeds, and the question will really be, where does this advanced GTF finally end? Does it end on a new single aisle or a future wide body? And the timing there will depend on what's available and where we are from a sense of availability in terms of engineers and resources in terms of investment.
Now, in the short term, you seem to have your hands full executing on 5 new programs with 12 applications. So,
yeah, we're busy as a bee right now.
I can well imagine.
We've got 5, as you said, 5 airframe manufacturers. We've got 12 aircraft models that we're powering with these 3 fundamental engines that have 6 engine models tied to them. And we're going to be busy for at least the next 3 to 4 years just executing on our current programs, which is really our key objective, is to execute on what we have before we worry about what the next opportunity is out there.
One of the advantages of the architecture is you end up with a fairly small and compact core. And as you move forward with getting a pressure ratio from 50 today to perhaps 65 or 70 in the future, you're looking at some very tight tolerances and some interesting technologies. To what degree does additive manufacturing come into that process, and how difficult is it to get your engineers to begin to design for adding metal to parts and coming up with unusual shapes that might be more efficient rather than taking metal away from parts as has been traditionally done and being constrained by manufacturing technology?
Okay, that's a boatload of questions. Okay, so let me try to dissect it one at a time. First of all, as we kind of look at going to larger gear ratios, that will really play better as you go higher in thrust. You know, at say a 40,000 or 70,000 or even 100,000, as we go up in engine size, there's more opportunity of shrinking or making a smaller dimension compressor or turbine because the size is still relatively large. If we were to try to do that at a 17,000 pound thrust class, we might get into some real dimensional constraints just because of how small those parts are. So the value of the gear really becomes more prominent as we go to the higher and higher thrust levels, first of all. Secondly, as we look at the characteristic of this gear system, and we want to go to higher pressures and higher temperatures. So therefore, things like material development, whether it's powder metals, or going to ceramic coatings, or new turbine alloys, whether a ceramic alloy, a ceramic material, or an alloy, we want to drive those temperatures up. But we want to do it in a way that's cost effective to both us as well as the airline, because we want the part to be long life, to be affordable, or from an acquisition cost, and repairable. So all those key elements are part of that. As we look at new manufacturing techniques, or repair techniques, because it can be both, but to start with the manufacturing side, there's a lot of advancements that we've made. You know, we use the term additive manufacturing or 3D printing. There's fundamental elements that come with those new techniques. You know, one element becomes the ability of designing or making very complex architectures that may be difficult to machine, or may be from a weight perspective not optimized because of how one would machine the part versus make this part by these new techniques. The other element becomes, which I think is more important when it comes to fuel efficiency, is the ability to go to some very complex contours, whether it's an airfoil contour or an internal passageway that's feeding lubrication into an area that we want to minimize the loss or the pressure decrease as that fluid is passing through that channel. There's ways of really improving either the aerodynamic benefit of how we bring air and fuel into the engine, or in some of the loss characteristics that may come with systems like a lubrication system or even a cooling system in an airfoil. So I think the additive manufacturing is going to have a big play, and depending on how that goes, in terms of how that capability develops, how does it play in improving time on wing or improving repairability? Because it could eliminate repairability from a sense it's cheaper to make than to repair, or it could expand capability by using some of these techniques to improve the repairability of a part.
Yeah, that was one of the questions, because you've got fewer parts on the GTF. Obviously, your manufacturing costs will be less, and hopefully maintenance costs to the airlines will be less as well. But as you get into these more advanced technologies, and you've got 24, I think was mentioned earlier, 24 parts on the GTF that are made by additive manufacturing. Hopefully those are also easy to repair or replace and keep maintenance costs low. Yeah. Have there been any benchmarks so far on maintenance costs through your testing, and how do you think the GTF will come out in terms of maintenance cost?
Well, we do monitor maintenance cost either by a part level or a subsystem level, so we can roll up to the engine level. And we believe we're tracking to our maintenance cost target. There's one thing I want to not correct, that's probably too harsh a term, but to amplify is, although we have fewer parts, they're all new technologies and in these new technologies, because the supply chain or the way we're producing that isn't at the volume of what we do today, even though fewer parts may not necessarily mean lower manufacturing costs. So that's a key element of how we're trying to manage costs today from an overall perspective. So as we look at how do we drive configuration, fewer parts is good for low cost and lower maintenance. This additive manufacturing can help us make the part more effective, or make the part at a lower cost, and that's a continual element of how we have to work. But these new technologies are a challenge for us. I mean, when someone asks me today, what's the greatest challenge we have, it's not in developing the product, it's getting the cost down to the target that we had established for ourselves several years ago.
Okay, so the GTF is not going to be a cheaper engine to buy, at least not initially.
It's not a cheaper engine to make.
Yeah.
I won't talk about, because I'll let the sales team decide what the selling price is.
Sounds great. With your major competitor has been touting their quote industry leadership unquote in ceramic matrix composites and cooling technologies. How would you say you guys compare with your competitors in that regard? And are you able to transfer some of the technology from your fifth generation military engines back into the civil side, or is that restricted by the government?
Well, I would say with our F-119 and F-135 on the JSF, certainly we have the ability of running very hot temperatures. So the materials, the capability is there. The question is that the right solution for a commercial jetliner where we're looking at really driving the best cost on a cost per flight hour operation? Mm-hmm. And while we are developing ceramics and we use ceramics for coatings, and we are developing ceramic, CMCs or ceramics matrix composites, the question becomes, are they the right solution? Because we're also in parallel developing new turbine alloys, and the value of the alloy is that it's a lower cost to produce and it has higher repairability. So the combination of a cost per flight hour, it's not clear to me that a CMC is a better solution.
Okay, great. Airbus has been discussing an A330neo and an A380neo with their customer, probably building on the success they've had with the A320neo. You mentioned previously that you can scale up. In fact, there may be some benefits of scaling up a GTF to that degree. With all that's on your plate, is that something you would contemplate in the short term? And is there a GTF or an A330 or A380neo a possibility in the near future, or is your plate a little too full right now?
Yeah, so as I said earlier, our prime focus first is to execute on the programs we have, and we're going to be busy for the next 3 to 4 years in terms of really developing product, servicing that product, or getting that product ready for service, with the latter models being the Embraer E2 going into service. So near term, we don't have the capacity to really go and launch a new business. So from a sense of jeopardizing the success of what we've been able to accomplish over the last 3 or 4 years. In the case of our next application, as I said earlier, our geared turbofan, we believe, does provide significant value to a wide body. The question is when. And we're really targeting more for like the middle of the decade. As I talked about this 10-year technology roadmap, we'd really like to bring our advanced GTF or our second generation GTF as part of that solution, whatever aircraft model it has. So near term, it's executing what we have, continuing to develop technology, share that learning or that capability with both Airbus and Boeing, and then to let timing and the market drive what is the next good application for us. There will be one out there, not sure which one yet.
Yeah. Great. Thanks very much, Bob.
Thanks, Aaron.